All right, thank you very much for the introduction, and very happy to be here at this conference. So today I'll be talking about some recent results on the approximation theory of deep learning and its interactions with dynamical systems. So ranging from approximating functions using deep feed-forward neural networks, and also approximating sequence-to-sequence relationships. So this includes recurrent neural networks. And we heard a lot about Residual computing, that's also related, and also some novel architectures that people use in deep learning today. So we'll start with some background. So we know that deep learning has achieved tremendous success in different application areas, computer vision, machine translation, NLP, and game playing. But from a theoretical viewpoint, there's a lot of very basic mathematical questions that remains quite a mystery to us. And in resolving these mysteries is really important because we're seeing some emerging applications of deep learning to new areas of science and engineering, in particular, physics and chemistry. And we really want to build a good mathematical theory for it. And today we'll talk about some very basic questions that has sometimes surprising, interesting answers. So to studying deep learning mathematically, one should really start with the question of what's really new here, right? So if you understand deep neural networks as a way to approximate functions, the problem of approximating functions using some hypothesis is certainly not a new topic in mathematics. Harmonic analysis, approximation theory has been studying things like this for a very long time. So what is really new here? I'll argue that one of the key aspects of new phenomena in deep learning today is this compositional or dynamical structures. So these present themselves in different ways. So in the first case, we can see that there's this composition structures that's present in the models, the deep learning models themselves. So deep neural network is a stack of many shell layers together, and this is, they're composed together. And then if you look at recurrent neural networks, you have this theoretically infinite number of repeats of these operations. So again, it's a compositional or dynamical structure. And this not just in the models, but also in algorithms and data. So for example, the very popular stochastic gradient algorithms and the variance, you can think of it as a stochastic process. So there's a dynamical structure involved in that as well. And when you have applications, especially in science and engineering involving time series or some other data that's generated from a dynamical process, then you also have this kind of dynamical structure in the data. And when you train these kind of models with dynamical algorithms and data, you really have some very interesting interplay between these structures that are present. And today we'll see some of that. So of course, I use these two terms interchangeably, composition and dynamics. And of course, in this community, we don't, this is kind of obvious. When you have a composition of a bunch of functions together, you can always write it as a discrete dynamical system and vice versa, right? So if you interpret the index of this composition function as some notion of time, then you have a very natural dynamical system. So this really connects deep learning, compositional structures, deep learning, and dynamics here. So that's the main source of connection. So today I will talk about only perhaps one of the most classical settings in machine learning, which is supervised learning. So what supervised learning attempts to do is to approximate some relationship between inputs and outputs. So the inputs could be images of cats and dogs, and the outputs will be the label associated with it. So this is a classical classification problem. You can also have sequence-to-sequence models where the input is some, for example, historical time series, and the output is the values of this time series in the future. All right, so there's a functional relationship between them as well. So the goal of supervised learning is to observe enough of this input and output pairs, and then to learn or approximate some target function that maps these inputs to the outputs. Okay, so that's the basic goal of supervised learning. And today I'll focus on, again, one of the most basic problems in supervised learning, which is the problem of approximation. So what is this? Imagine you have some target function that you want to learn, this target relationship. And so what we do is that we come up with a hypothesis space of possible candidate functions that approximates this target. So this could be linear combinations of basis functions, polynomials, or you could, in the deep learning case, this could be deep neural networks. Right? And the problem of approximation simply asks how big this hypothesis space is. Okay, so what is the distance between the best possible model you can get in a hypothesis with the target? Okay, so the gap between these two is called the approximation error. And this is how I'll define approximation error. So what are some basic mathematical questions you can ask in this case, right? So the first one is the so-called universal approximation property. So given some hypothesis space H and a target space which contains all the functions or functionals or whatever that you're trying to approximate, right? And the first type of result is universal approximation, or mathematically you can understand it's a density result. It says that for each target function in my target space and some allowance epsilon, can I always find some function in my hypothesis space, I call it f hat, such that they are close up to epsilon, okay? So if this is true, then of course we know that this H is dense in C under this norm, okay? So that means you can learn some arbitrary relationships in your target space. But this is not the only kind of questions we can ask. We can also ask the second question, which is approximation rates. So given that your hypothesis is dense, but suppose your hypothesis space contains some measure of the size of approximation budget, right? So I call this M. Okay, so M, you can think, for example, in neural networks, M could be the width or the depth or both of your network. And in the case of Fourier series, M could be the number of orders of your cosines and sines. So this measures the budget that you have for approximation, and approximation rate simply says that given a finite budget M, what is the best possible approximation error we can get? Okay, and this usually contains two terms. One measures the complexity of my function f star, my target function, under this hypothesis space. Okay, so this tells me, what kind of functions that are easy to approximate using my hypothesis space. And this rate function just tells you how fast the error actually decays to zero. Okay, so both of these are very important. In particular, this complexity measure really tells you, what your hypothesis space is good at approximating. Okay, and that reveals a lot about your hypothesis space. So let's start with a very simple and hopefully familiar example to illustrate what are these two types of results, right? So we consider this target function space to be just periodic, alpha continuous differentiable functions, and our HM, our hypothesis space of complexity M, is simply the trigonometric polynomials of order M. Okay, so this is like a discrete Fourier series, and so we know the following results, right? So the density result, you can simply deduce it from the Weierstrass theorem. And in fact, you can say a little bit more that Stone-Weierstrass theorem actually gives you some sufficient conditions for any hypothesis space of kind of a polynomial form to have a universal approximation, okay? So this is the first kind of density result. And the second result tells you the approximation rates. And this is a very classical result due to Jackson. It says that if I limit the order M here, then what is the best possible approximation error? You can show that this is a bound of the approximation error. And you can see that the complexity is measured by simply you can think of it as a Sobolev norm of f star. So the smoother the target function is, the easier it is to approximate using Fourier series or like trigonometric polynomials. So this is well known in approximation theory. So this tells you that these smooth functions are simple, and of course you have m to the alpha, which tells you that the rate becomes larger, the better, faster if you have a smoother function. Okay, so the insight here basically says efficient approximation is possible if this function is smooth and has small gradient norm. And in fact, you can prove the only if statement as well. Okay, so that's one example. So our goal of this mathematical theory is to develop this kind of Weierstrass, Stone-Weierstrass type and Jackson type results when this hypothesis space and the target space perhaps have compositional and dynamical structures like deep neural networks, right? So what changes there? Okay, so the first part I will talk about a approximation theory of deep learning from the static viewpoint. It means, this is dynamic viewpoint, but it's a static problem of approximating certain functions. So this will be feed-forward neural networks. If you look at shallow neural networks, which you can understand as some sort of nonlinear approximation method, but it still uses linear combinations of basis functions, just that these basis functions are trained, right? So the way that you increase complexity in shallow neural networks, and in fact, all these basis linear combination-based models is increasing the width, so the number of basis functions. Okay, and this we have a good understanding of how what functions are easy to approximate when you increase this width level. But a deep neural network increases complexity in quite a different way. So instead of building complexity to the width, you build complexity through a number of compositions, or you can think of as longer dynamical evolution, and it increases complexity this way. So then one very natural question we can ask is, what is the equivalent kind of Weierstrass theorem for universal approximation when you increase complexity through depth, right? That would be an interesting question to ask. So the way we're going to approach this is a continuum method. So we know that this deep neural network, right, there's a lot of different compositions and nonlinearities, and it is hard to analyze in general. But this is not the first time we see this kind of problems, right? If you think about solids and fluids, at the atomic level, they are also discrete structures, and then they interact with each other nonlinearly in a very complex manner. But we sort of take a zoom out. We zoom out from the atomic level and look at some mesoscopic scale, and we can then idealize them as some continuum equations, like the elastic equations or the Navier-Stokes equations. So we can do the same thing and take a deep neural network here. This time it's a residual neural network. So this F is simply the kth layer nonlinear function, and the theta k is the weights at each layer, right? So we can take this, and then we can idealize it by treating this layer coordinates, the layer index values as a time index, and this will become a continuous forced dynamical system, or you can think of it as a control system, where theta t is now a control. So this idea was first proposed in 2017 in this paper, and analyzed in these two papers on how to build good stable architectures for deep neural networks, and also how do you build training methods for it. And later, of course, in the machine learning literature, this is made very popular as neural ODEs. Okay. So the first, we might wonder, like, how can this dynamical system, right? So we are approximating some functions, which is the relationship between input and outputs, through a dynamical system now, right, under our viewpoint. So the question is, how can dynamics actually approximate functions, right? How does it actually work? Now I have a very idealized situation that shows you perhaps this is how it works. So okay, maybe I'll say it first. So you can see this is a binary classification problem. So you have a bunch of points, and you want to classify them. Basically find a boundary of these two sets, and so each color is a different class. And you can see this is not linearly separable in the sense that you cannot draw any linear classifier in 2D and basically split them, right? They are intertwined together. And what I'm going to do is to first write down this dynamical system, okay, that evolves these points. And so each of these points is an initial condition of a common dynamical system. And I'm going to run it through this dynamics. And let's see what happens. Hopefully this works. Okay, so you can see that the dynamics actually drives the system to a different setting, so a different configuration, such that these points are now distributed in a very different way, and they're rearranged in some sense. And now you can simply classify these points using a linear classifier. Okay, so this tells us that maybe the way we can achieve approximation of functions through dynamics is to rearrange the domain in a certain way, so that at the end you only need a very simple layer or transformation at the very end to approximate this function. Okay, so let's try to make this a bit more precise. So suppose we have a target function f star that we want to approximate, and that maps some x to y. So what we're going to do is to take this x and set it as the initial condition of a control dynamical system. So this system is x dot equals ft xt. So ft is chosen from some family of functions which are called curly f. Okay, so this is a family of functions and this basically tells me, this f curly f basically determines what kind of dynamics I'm allowed to use. And so this will transform the inputs x0 into xt, okay? And then at the end, I will simply use a terminal family of functions g to produce a output y hat that will be close to y. So usually this g family is very simple. For example, linear classifiers or linear regression. You can think of it as the last layer of a neural network. And this is really basically all the residual layers in between. Okay. And this hypothesis space then, of course, is controlled by this F, which is a kind of controls that you can apply to this dynamics, and the terminal time t, and then of course g. So we can write down this dynamical hypothesis space, which call it HFG, which is simply the composition of this terminal g with your transformations phi. So this phi will be inside this flow maps of this control dynamical system. Okay, so you can think of this as a continuous idealization of a deep residual neural network hypothesis space. Okay, so then the question is here, can we have some general sufficient conditions, very much like the Stone-Weierstrass type of result? What kind of F and G will be enough to give me a universal approximation? Okay, and here we have some results. We can show some sufficient conditions for universal approximation, and for dimensions at least 2, we simply only need these 3 conditions. Okay, so the first one is that the terminal family G must cover the range of your function that you're trying to approximate, because it is composed together, so the range never expands, right? So you need the terminal function to have enough range. And the second one is that this family of control functions that you apply to your residual neural networks, they have to be restricted affine invariant. So this is a weak version of affine invariance. Basically says that if you apply some affine transformation to your input and then apply the function, that function should also live in your control family. And the third one is perhaps a more interesting one. It says that the closure on the convex hull of your control family, your right-hand side of your neural network, you can think of that, it contains a function we call a well function. So what is a well function? It's simply a function that is 0 in a convex set and non-zero everywhere else. Okay, so why is this function important is if you think about it, this kind of functions allows you to drive points in an arbitrary way, because you can place some points in the middle and they won't move, right? Because it's 0. And you can move the points that are outside of these points. So you can think of it as instead of point separating property like the Stone-Weierstrass kind of argument, this is like a point transporting property. So once you have this kind of functions, you can then show that you can use the dynamics to build essentially arbitrary functions. So you can achieve density in LP by simply having this function. Okay, so this is the kind of results. And of course, this is for dimension greater than or equal to 2. For dimension 1, there's a slightly weaker result, because in 1 dimension, the ordinary differential equations, they preserve these topologies, right? So they cannot, the trajectories cannot intersect. So there are some limitations here in 1 dimension. So you can only approximate increasing functions. Okay. And there's very interesting connections between this kind of problems is in the sense that whether you can use a control system to drive points into arbitrary configurations. This is a very much studied problem in controllability. So there's some recent work in this area about using controllability kind of arguments to derive some universal approximation results. But I'll emphasize that in this case, we're looking for some sufficient conditions, not just studying a particular controllable system, but really looking for some sufficient conditions that any architectures can achieve this. So these conditions are rather general. You can check that a lot of architectures you use in deep neural networks do satisfy these properties. So a further work that we have done here is that we can consider functions that are invariant. So suppose that we do some permutation to the index of a function, index of the input to a function. So this Sx simply transforms a input x by permuting its indices in a certain way. So this S is simply element of a subgroup of the permutation group. So one example will be if you think about functions that are invariant with residual translations. So this will be one very important application is a convolutional neural network, right? So if you use a convolutional net and with a pooling layer at the end, this is invariant, and this is very good for classification of images because you're supposed to have your classifier is supposed to be invariant with residual translations for most of the time, right? But you can also have other kind of subgroups. For example, deep sets they deal with a case where this symmetry is entire symmetric group. So this is where you want to learn functions that are not functions of a vector, but really a function of a set right? So it doesn't matter how the vector is arranged, the elements are arranged, they should give the same values. So there's a lot of interesting application of this. And here I give another example of a different kind of subgroup for the permutation group. So this is where you want to, for example, you want to predict the property of a certain material, and this material is in this called CIF data form. So you can think each row represents an atom, okay, in the lattice, and so each of this is atom, and each row here is the x, y, z coordinate of this position of this atom in the lattice. Okay, so this, you can think of this as describing a lattice structure, right? And what's interesting here is that if you exchange the rows or the columns, it's essentially describing the same architecture, right? And if your property is invariant to rotation translations, then of course, if you change these columns or change these rows, you will not affect the property because you're describing the same material. So in this case, you can think of the permutation group as a product permutation. So if you look at this entire table and regard it as a vector, if you flatten them, then if you change each of the rows and columns, you don't change the output of the property you're trying to learn. And in this case, this group would be a product of two symmetric groups. Okay, so D1 is the number of rows and D2 is the number of columns. So this kind of functions arise very often in applications of machine learning to let's say material science. And the question is, how can we build networks that respect this kind of symmetry, right? And we can basically extend what we showed before and derive a similar set of sufficient conditions of a universal approximation, but this time with the arbitrary transitive subgroup of this permutation group. Okay, so we can build invariant functions. And this is a good way to build invariant functions, in my opinion, because if you think about it, invariant functions, they are restricted, right? Because you need to respect these invariants. So you cannot have your layers to be too complex, okay? If it's too complex, then you lose this invariance property. Right. But at the same time, you really want your network to be universal approximators. You want to approximate arbitrary relationships respecting this kind of invariance. So deep neural network is a very good way to do it because you can make each layer to be simple and respect the symmetry, and just increase the number of layers, and that gives you symmetry for free because this invariance commutes with composition, and then together you can build a very complex networks that still respect the symmetry. Okay, so this is a very good way of building invariant functions. Okay, so so far we talk about like a Weierstrass type of results. I guess it's much weaker than Stone Weierstrass because it's not if and only if we only have sufficient conditions. But we have some results here for dynamical and compositional hypothesis space. And what about this Jackson type of results, which tells you what functions are easy to approximate? So this in 1D we have obtained some rates in this case, but in general, this problem is much more complex, and maybe you can hear other talks that talk about this as well in the coming days. So it really requires the identification of the right function spaces and the complexity measures, what functions are easy to approximate by these dynamical structures. And it has some connections with control theory, dynamic barren spaces, and also compositional features that could be present in your network. In your target function. Okay, maybe I'll say just a few words on this. So far we only talk about the approximation theory, but the continuous setting actually allows us to analyze also the training or the learning or the optimization process of deep neural networks. And this optimization process basically is optimizing a control system over this ways, and minimizing some loss, right? And could be regularized. And if you look at this, if you're familiar with control theory, you can see that this is very much like a control problem. And in fact, it is a control problem in the mean field sense. And we can actually derive some, necessary sufficient conditions or optimality from the optimal control viewpoint. And also we can develop some new algorithms based on this control view of this deep neural network idealized dynamical system. Okay, so I will not talk too much. It's nothing to do with approximation theory, but you can do that. Okay, so for the second part of my talk, I'm going to discuss the approximation theory of deep learning, but this time not just approximating functions, but approximating sequence-to-sequence relationships. So as we saw before, sequence-to-sequence relationship has a lot of applications involving, for example, time series prediction. We have heard a lot about climate weather prediction, so that's one example. And in natural language processing, translation between two languages, you can think of it also as a sequence map, where the sequence index is now the index, the position of the word or the letter in the sentence. And of course, you can also think of control systems as a sequence-to-sequence relationship, because if you apply a control, you can think of the control as a temporal sequence, and then the response of the system, perhaps satisfying some controlled differential equation, is again a response. So this is another mapping between the control and one sequence to another. Okay, so in the deep learning literature, there's a lot of different type of models or architectures proposed for this sequence-to-sequence learning problem. So including recurrent neural networks, and also some convolutional based structures like the WaveNet, and also encoder-decoder type or attention type of architectures like transformers. So they're all doing sequence-to-sequence modeling. And a very important question we can ask, at least from the theoretical viewpoint and also in the practical viewpoint, is how are they really different, right? When should we use which? What are they good for? And are they really essentially different approaches to modeling sequences? So we hope to get some answers in this direction. So modeling this kind of static function relationships and sequence relationships are essentially different in the following way. So in the static setting, you have some input and output vector. They're just vectors, and your target function is just an ordinary function, over vector spaces, finite dimensional vector spaces. But in the dynamic setting, your input is now a sequence of vectors, and this k you can think of as a sequence index, right? And your goal now is to, and of course the output is also a sequence. And now the target function is basically not just one function, but a sequence of functions. So for each index k, the output yk can potentially depend on the entire input sequence, right? So and this could also depend on the time index k. So this h star k is actually a functional, okay, that maps this input to the output. And the goal of supervised learning in this case, instead of learning a function f star, you're now learning the sequence of functionals h star k, or you can also think of as operator. Okay, so then the approximation theory for sequence modeling, our goal is to derive very similar statements to Jackson's theorem, but this time the target space will be some suitable classes of sequence relationships you want to identify, and H is the different architectures like recurrent neural networks, convolutional nets, and so on. Okay, and our goal is to answer some of these questions. So what kind of sequence relationships can we approximate, and what kind of sequence relationships can we approximate efficiently? Okay, and how does the complexity measure or the rate depend on different hypothesis space? So what are they good for, right? And then of course this will lead to the answer of how to choose which ones to use in practice by looking at the problem. So I'll mostly talk about recurrent neural networks, and in the end I'll summarize some similar results that we obtained for the other architectures. Recurrent neural network is one of the most classical ways of building a sequence-to-sequence relationship. So the idea is that you want to map one sequence to another, and you want this to have some memory components. So it's not just, for example, each output might depend on some historical information on the input. So one way to do it is to introduce a hidden dynamical system, HK, okay, which evolves according to a dynamics that's parameterized by a neural network. So this sigma is the activation function, and this is the usual affine transformation. And the inputs enter the dynamics as a forcing term, and the output sequence is simply a readout of this dynamics. So we have seen a lot of this in the reservoir computing case. So in the reservoir computing, W and U will be random matrices, but here we can allow it to also adapt to the data. So this, of course, parameterizes a sequence of functions together. So each Y depends potentially on the entire history of X up to this point. Okay, so you have a sequence of functionals. And here we're going to take, again, a dynamical idealization of this and interpret this K as time, and then take a continuum limit. So we can obtain this kind of basically replacing this K by a continuous variable time. So everything else remains the same. And now you can see that this kind of continuous time recurrent neural network parameterizes a sequence of functionals now together, right? That maps my entire input sequence into my output sequence. So this is not just a conceptual idealization, because a lot of problems where the time series is irregularly sampled, this could be a good way to handle it. So empirically, we found is a kind of empirical fact that RNN performs very poorly when modeling systems with long-term memory. Okay, and whatever that means, it's not really very precise. But usually, one understands this term by saying that the output depends on some input features from a pretty long time ago. That's what long memory means. So the idea is that can we actually make this precise, and can we investigate this phenomenon more precisely? So what we're going to do is to start with the linear case and see what we can say about it. So we simply let the recurrent activation be identity and see whether we can make this statement about long-term memory more precise. So here we simply have a linear dynamical system, and the nice thing about having this linear RNN hypothesis space is that you can write down the solution. So this RNN hypothesis space is simply a class of linear functionals. They are in the form of a convolution between a kernel and X, where the kernel is the sum of exponentials. Okay, so this is an exponential matrix multiplied by U. And we're going to consider only stable RNN, so this W here will have a negative real parts, this Hurwitz matrices. You can show that this is necessary for you to be a continuous functional. Okay, so let's take a look at this hypothesis space, because we can write it down exactly. You can already see that there are some properties of this functional. So first of all, each of them is continuous and linear. It is causal in the sense that it doesn't depend on my input in the future. Right? This is obvious because your ODEs are causal. It is a regular function. This is a technical requirement. It's not very important. And the family hat is time homogeneous. So time homogeneous here, I simply mean that if you shift the input sequence by a shift in time, and the output sequence also have the same shift. There's no special point in time, and then you can also understand it as sort of linear time invariant dynamics. Okay, so these are some properties you can immediately identify about this RNN system. And the first result you can show is that the converse is, in a sense, true, in that any functional satisfying these relationships can be approximated uniformly by the recurrent neural network. So this is a density result. So here's the result. If we let any family of continuous, linear, causal, regular, and time homogeneous functional, then we can approximate it uniformly in time and uniformly in the inputs by our recurrent network. So the idea is very simple. We can show that if your target functional has these properties, then you can prove that there is a common representation for the entire class of sequence of functionals. And if you compare the representation with our RNN hypothesis, they are very similar, and it basically reduces to approximating this representation function rho by our exponential sum function. Okay, and this becomes a kind of a simpler problem in approximation theory that we can analyze. Okay, so this is a density result, but of course we want to ask, can we get some sort of Jackson type of results, which says that, what is the approximation rate of functionals? What functionals are easy to approximate using our recurrent neural network? Now, this is in some sense very important because we want to really tell the difference between different hypothesis space. So density result is not enough, right? We want to identify some rates. So here, it turns out that this rate actually depends on these two concepts: smoothness, which is a very classical concept, and also memory. So what are these two concepts? I just illustrate with a plot. So these are two classes, sequence of functionals. So the input is the same, but they produce different outputs. So the first one is smooth in the sense that the input is smooth and the output is smooth in time. But the second one is not quite. The input is very nice and smooth in time, but the output is kind of jagged, right? So this is a non-smooth functional. And also there's also a notion of memory. So if you see that the input has stopped changing about halfway through, right? And then the output responds pretty quickly and also stops changing about the same time. Okay, so in other words, this doesn't really remember what happened before, but this one continues changing in time. Okay, so this suggests that there is some memory that is being retained by this relationship. Okay, so of course we can make this precise by simply defining the following. So we let EI be the standard basis vectors in RD. And we have this bold phase EI to be a kind of impulse signal that is equal to 0 when time is smaller than 0, and at time 0 it steps to 1 at direction. So it's basically like a flat signal like this. Sorry, like this. And we feed this signal into my functional, and we observe its effect. So we kind of query the functional with this kind of signals, and we simply define the smoothness as the smoothness of this mapping of this output of this signal. Okay, so how smooth this part is. And memory is measured by the decay rate of the derivatives of this map. Okay, so we can make this basically what I said here precise. And with this definition, we can prove a Jackson type of result. Okay, so this is the result, and I just want you to focus on this part. So the key assumption here is that we assume this memory term, which is a derivative of my action of my functional on constant signals, it decays like an exponential. So if you multiply by exponential, it's still a small o1. So if you have exponential decay of these derivatives, then you can determine a rate like this. Okay, so let's take a look at this rate. So here, this is a rate, and the smoothest dependence, this C alpha m to the alpha, is familiar. It's the same as the Jackson's theorem for polynomial approximation. But the beta part is new. Okay, so we assume that the memory term, like the derivatives of this guy, is the e to the minus beta. Okay, so this is a derivative here. Sorry. So there's no curse of dimensionality here due to linearity. So we have some linear functional, so we can simply approximate each dimension separately and add them together. So there's only a linear term in dimension here. But hidden, this is a curse of memory. So why? Because we assumed that the derivative falls off like e to the minus beta t. But remember, in our density result, we didn't have this assumption, right? And we needed this assumption to get a rate. So the question is, what if it doesn't fall down exponentially? For example, if my this is again a derivative. So if the derivative falls down like t to the minus omega, then what we can show is that to get approximation error epsilon, you need an exponentially large number of neurons in this case. Okay, so in this case, this is a curse of memory. And this is, of course, consistent with some fading memory properties that people have discovered in the reservoir computing case. So to summarize, the insight is that we have efficient approximation if my functional is smooth and has exponentially decaying memory. And this memory is basically the derivative of this map on constant signals. Okay, so if it decays exponentially, we have good approximation. So it turns out the only if part is also true. That means we can, if we assume that some functional or class of functionals can be approximated uniformly and nicely, like with the rate that we had before, by recurrent neural networks, then we can show that it necessarily have exponentially decaying memory. All right, so this is in approximation theory, this is called a Bernstein type of result. It shows you that only exponentially decaying memory functions can be approximated by this linear recurrent neural networks. Okay, I should also mention that this is about approximation, but what we can show in these papers is that a similar curse of memory also holds when you try to train these neural networks. And this is something that we know in practice. If you have a long-term relationship, when you try to train these neural networks, you have this very long plateauing behavior of the training. And here we can make this precise. In this case, why it happens. It has something to do, again, with this memory. So when you increase the memory, the training slows down exponentially as well. Okay. And up to now, all these results are holds for linear functionals with linear RNNs. Okay, this is kind of a tremendous simplification. So you can ask whether nonlinear recurrent activations, for example, adding a tench to your dynamics, does it actually alleviate this issue? And in terms of the answer is at least in many cases is negative. So we show that this, for example, this inverse approximation theorem still holds if you add a tench activation. That means even if you have a nonlinear tench activation in your recurrent neural network, it can also only approximate linear functionals with decaying memory, right? So in other words, simply adding a nonlinearity to your dynamics does not fundamentally change the memory pattern. So the idea is quite simple, because if you look at this kind of tench activations, if your network becomes stable, then eventually its derivative will go to some area that's close to the linear part. Right, so it will behave very much like a linear system. And if it doesn't behave like a linear system in terms of memory, then it has to saturate. And in that case, you will not be able to learn very complex relationships, because all the hidden states will be +1 and -1, this derivative. right? So we can make that precise by constructing certain Lyapunov function arguments and show that this is indeed the case. It doesn't change the memory pattern. But of course, you can change the memory pattern by changing the form of your recurrent dynamics directly, right? So instead of just changing the activation function, you can modify the right-hand side of your equation, for example, into LSTM or in a GRU, and that may change the memory pattern. So this is something that remains to be answered. Okay, so I'll end off with the extension of some of these results to the other architectures, because this kind of functional or sequence functional approximation framework is very useful because it allows us to also derive similar results for other architectures and see what's different. Okay, so one popular architecture is the so-called WaveNet that's very often used in text-to-speech kind of applications. So here we're still mapping two sequences, one sequence to another, but instead of introducing some hidden dynamical system, you simply do dilated convolutions, many different layers of dilated convolutions to obtain the final result. Okay, you can see that it's again a causal map because it's one-sided convolution, but of course you have very different properties, right? Another kind of architecture is the encoder-decoder type of architectures. So this is where, for example, on the left-hand side, you have an input sequence and you feed it into a recurrent neural network. But instead of reading the output sequence out directly, you simply use this recurrent neural network to code it into some context vector, a coding vector, okay? And then you take this coding vector and feed it into another dynamics, which decodes it and produces the output sequence. So this is the working principle of this kind of architectures, and it's different from recurrent neural networks. And transformer is another version of this encoder-decoder, except that you don't have these recurrent connections. Okay, so you can see that they're all mapping sequences to sequences, but they're different. But how are they really different? And when do we use which? We can try to answer some of this in the simplified settings. So here's basically the punchline. So we can show that they all achieve density in appropriate functional spaces. Okay, but the Jackson type of results are different for each one of them. Okay. Efficient approximation depends on different notions of complexity. So in the recurrent network case, we already saw that this depends on some exponential memory decay of the target, right? You can approximate it if and only if it has exponential decay in memory. But CNN's, the WaveNet, is different. It relies, in a sense, on a sparse dependence on inputs of the outputs. So if you change the inputs by a little bit, the outputs should only change at specific locations. So the dependence on input and output should be sparse. And if you think about it for the applications of WaveNet, it makes sense. If you look at a text-to-speech program, if you change the text or the speech at select locations, then the output should only change also at some specific locations. And you can make this precise by defining some tensorization rank. So I'll not go into the details, but you can take a look at our paper here. And finally, we can also take this setup and analyze the recurrent encoder-decoder, which is this architecture that we talked about before. You summarize the sequence into a context vector and you decode it. And in this case, we find that the functionals that are easy to approximate are precisely those where the output only depends on some global features of the input. That means if you change the inputs, by adding some random noise, in the end, it doesn't really change the output in the same way. So the output only shifts. For example, the mean will increase by a little bit, but it will not have very, like this kind of localized dependence. And this one, we can make it precise by some arguments that are similar to POD, principal orthogonal decomposition. So we have some low rank property as well. So what is punchline here is that, in fact, if you look at all of these properties, so these properties are those functionals that are easy to approximate using our method, our architecture. These properties are precisely properties of these architectures themselves. So a stable recurrent neural network has exponentially fading memory, and the convolutional network has sparse dependence on inputs, and the recurrent encoder-decoder has this global dependence features because they are all summarized into a small feature vector and then decoded, right? So the temporal information are actually summarized in the static vector. So these are features precisely of the networks themselves. And it turns out that then they are really good at approximating relationship with the same kind of features, right? So the punchline here is that you really need some structural compatibility, and these structures are dynamical, between the model and the target for you to have good approximation. Okay, so this is the lesson we learned. But of course, there's a lot more to do in this area. So here are the references of the papers I talk about here. You can find the slides online, I think. So I'm happy to take some questions.